Hi, and welcome to my talk on exploring replica-enhanced environment transitions along the reality-virtuality continuum. My name is Fabian Pointecker, and I'm a researcher at the University of Applied Sciences, Upper Austria. The current procedure for most VR applications is that the user puts on the headset and directly starts in the desired target VR environment. The user's whole field of view is completely virtual in a fraction of seconds. This approach involves a direct and abrupt change without any assistance for the user. We therefore investigated how to enable a seamless engagement from the real environment to virtual reality, as well as back from the VR environment to the real environment. Such seamless approach should enhance and support the user experience when engaging with a VR environment, particularly for users with limited HMD experience. Existing research has investigated various aspects of transitioning between virtual reality environments, such as scene changes within VR, or improving engagement through the use of replicas, or evaluating transition techniques to move between individual stages of the RV continuum. Our novel approach integrates all these approaches by utilizing a replica and deploying transitions techniques across multiple stages of the RVC. To realize such transitions, we made use of recent advancements in video-based see-through head-mounted displays, such as Apple, Meta, or Vario devices. Those HMDs are equipped with high-resolution front-facing cameras with a large field of view and acceptable latency, which allows to perceive all stages of Milgram's Reality-Virtuality continuum within a single display without changing the headset. I will now describe our generic concept of a seamless transition process to facilitate a seamless and comfortable transition between the real environment and a fully virtual environment. We designed a novel transition procedure that utilizes the entire RVC by employing a replica. This concept aims to visually support the total engagement into and exit from a target environment in VR, enabling a supportive and understandable transition. After putting on the HMD, our approach starts in the VST mode, without any virtual content. The VST mode offers a real-time video stream of the environment, ensuring that users see the same content as they would without the HMD. The user can remain in the real environment for any desired duration. If the user feels comfortable, the transition process is initiated by the user. The user is now progressively introduced in the VR environment. The virtual component on the RVC is incrementally increased, starting with the steadily growing number of digital replica objects. During this process, the real world is progressively overlaid with virtual replica objects, which are aligned with their real-world counterparts. The user is now perceiving the environment in augmented reality, until only a small part of the real environment is visible, which describes an augmented virtuality state. The proportion of the replica increases until the environment is complete and the user finds himself in VR. At this point, there is a moment when only the replica is visible, and the duration of this phase can vary depending on the specific implementation. A longer waiting time allows the user more time to process the replica, but also extends the overall transition time and may impede the flow. The transition process is not yet completed, as most VR applications don't use a replica environment. Instead, we are now progressively introducing the target environment, which depends on a specific use case. The replica environment is now getting continuously dismantled, while simultaneously constructing the target environment, allowing it to emerge stepwise. Once the target environment is fully established, the transition procedure is complete. The replication of the real environment plays a crucial role in achieving a seamless transition process. On the one hand, this allows the user to be initially transferred to a familiar environment that is already fully virtual. On the other hand, all visual effects can only be applied on virtual objects. For example, a fade effect cannot be applied on a real desk, but when using the replica, a fade effect on the virtual desk will look as if the transparency of the real table also changes. To achieve the impression of a realistic lighting in the replica, we implement coherent lighting. This further enhances a smooth transition by consistent lighting conditions throughout the whole transition process. We simulated the sun as the primary light source, and the color gradient in the replica is based on a video from the pass-through cameras. The position of the sun is determined based on the current GPS coordinates and time. Leveraging the available knowledge of room and window geometry, the actual angle of sunlight entering the room and the resulting shadows are simulated. Real-time weather data is also incorporated into the simulation, allowing for the representation of sun, cloudy skies, rain, and snow, and to prevent direct sunlight. To accomplish this transition process, an object-based transition technique is required to provide a procedurally transition for each environment. Based on related work on transition techniques, we identified 4 promising transition techniques. I will now describe the design and concept of each technique, starting with fade. Instead of immediately switching on or off the virtual objects, the fade transition gradually changes the transparency of the virtual objects and continuously replacing their corresponding counterparts. Once the replica has been fully faded in, the object within the replica will progressively reduce their visibility, while the objects from the target environment will begin to emerge, as the transparency is successfully decreased until the entire target environment becomes fully visible. For the next transition technique, we decided to use a technique that is more visually prominent to enhance the user's attention during the transition process. Instead of the rather subtle and visually simple fade, the dissolve transition disintegrates or materializes objects within a burning or flooding effect on the surfaces. The visual effect manifests as a randomized noise pattern spreading across the objects. The choice of the translate technique is inspired by real-world metaphors, where shutters and blinds can be opened or closed by sliding them. This transition technique involves the movement of objects into or out of the environment to facilitate the transition between the environments. While this may be a realistic behavior for blinds and curtains, as it is expected for them to move at some point even without user interaction, it may not necessarily apply to objects like tables or walls. For our last technique, we selected a combined approach of all 3 previously described transition techniques to highlight the strengths of each individual technique. We applied fade on large surfaces such as walls or floors, as it is less notable and therefore less distracting when transforming such large objects. Dissolve is applied to objects closer to the user and objects that require the user's attention, such as tables and chairs. These objects also define the boundaries of the space and potentially obstacles in the real environment. To achieve an authentic impression, translate is used in a replica for blinds and curtains, as these are also used in a similar way in the real world. This should increase the credibility of the replica. To validate our approach, we conducted a user study, retrieving qualitative information about the user experience of the overall transition process, comparing the 4 transition techniques to a baseline condition, as well as first qualitative insights into the relevance of visually coherent lighting in the transition process. We used a pre-study to validate the study design and prototype parameters and collect initial feedback. Reported issues and problems were incorporated in the further concept and integrated into prototype for the main study. For the main study, we used a within-subject design and recruited 16 participants. For counterbalancing, we employed a balanced Latin square test design. For quantitative analysis, we used a short version of the user experience questionnaire to gather comparable scores for user experience. We also employed the fast motion sickness scale to make sure that all participants were feeling well and could abort the study when necessary. After each transition, we conducted a semi-structured interview to gain exploratory insights into efficiency, usage scenarios, emotional response, and spatial orientation. Recent research showed that user experience regarding transition techniques between AR and VR relies on the specific use case and can be categorized based on professional and non-professional context. In order to cover both application areas in our user study, we decided to implement two different environments representing both areas. Target environment 1 represents a medieval scenario, and target environment 2 showcases a classic office environment. To utilize the transition from the real world into VR, we applied a simple search task, where participants had to search for an object in the target environment, which was shown to the participants on a printout in the real environment. I will now describe our results and main findings. In terms of user experience, all transition techniques received an overall score greater than 0.8, which is considered a positive evaluation result, except for the baseline condition, which was evaluated neutral with an average score of 0.3. We also found a significant difference for the overall scale. There, the post-hoc tests revealed that the baseline condition was rated significantly lower than the combined condition. Insights from the semi-structured interview revealed that fate is simple and effective, but boring and sometimes confusing, as there are lots of elements visible simultaneously during the transition. Dissolve is visually prominent, and participants mentioned that it can guide the user's attention and make the transition clearly notable. But the amount of visual change in the participants' field of view was considered too overwhelming. With Translate, participants felt that it supports spatial orientation in the target environment and found the incoming objects pleasant. But it was also received as uncomfortable or even threatening, especially when it comes to large flying objects. Combine worked out as we expected. Participants described it as a suitable compromise between visual load and visual guidance. Users positively remarked that it combines the best aspects from the other three techniques. Participants liked that we used the dissolve pattern on objects that require the user's attention and the fade effect on larger objects to reduce the distraction. Interestingly, participants that did not like Translate in its standalone version liked the effects in the combined condition, as we only applied it to objects that would naturally behave that way. The user study shows that participants appreciate the replica as an intermediate step during the transition. This is also reflected in the rankings for user experience. Participants who found the replica inefficient at first even changed their mind during the course of the study, as they expressed during the interview. The use of the replica allows users to get familiar with the environment and makes it easier to follow the transition. The coherent lighting was only actively noticed by one participant. Other participants felt that the lighting should be similar in terms of brightness and direction, but that there is no need for identical lighting in the replica. Moreover, one participant suggested to slowly adjust the brightness in the replica from the realistic illumination to gradually match the light source of the target environment. Some participants pointed out that the transition duration is too long, as despite it in other publications, the duration for transitions can range from a few seconds to 50 seconds or even 60 seconds. The preference for duration depends on the individual user and the specific application context. In contrast to traditional 2D visualization recommendations, our transition process distributes visual load across the entire field of view of the HMD. In order to prevent users from feeling overwhelmed during this process, which could adversely affect the overall transition experience, we opted for a more cautious approach in determining the duration. One participant even noted that in case of infrequent transitions, a longer transition duration is appropriated. In this work, we conceptualized, implemented, and analyzed a generic concept for transitions to a target environment across the whole RVC, as well as a digital replica of the real environment. Furthermore, 4 specific transitions were implemented and compared to a baseline condition in a qualitative user study. Future work should include different transition techniques, such as morphing and visual landmarks that provide spatial orientation. Furthermore, visual coherence should be explored in more detail, as well as potential application areas. Future work can investigate different variations of the combined technique using a comparative quantitative approach. Finally, the transition should be included and examined in a real-world use case study. For more information, please have a look at our paper and do not hesitate to contact us. Thank you for your attention.